Until the days of supersonic speeds and the jet propulsion of rocket ships, the propeller is a relatively efficient method of moving our airplanes through the air up to speeds of 500 to 600 miles per hour. In general, the size of a propeller is dependent on the power of the engine. This relatively small engine can turn a small propeller. This larger engine needs a larger propeller to absorb its greater power. If still more powerful engines were equipped with two-bladed propellers, they would be so large that the blades would touch the ground or else require a lighting gear of excessive height. Therefore, three-bladed propellers are coupled to medium-high horsepower engines, while four-bladed propellers are usually found on superpower engines, about 2,000 horsepower. Most aircraft mount tractor propellers on the front, where they pull the airplane along. Some, however, mount pusher propellers that push the airplane somewhat in the manner of a steamship propeller. Since a propeller blade is fundamentally an airfoil, it may be helpful to review airfoil principles. An airfoil with direction of movement like this produces a lift or force like this. The angle that the chord line of the airfoil makes with the direction of movement is called the angle of attack. The efficiency curve of any airfoil, sometimes called the L over D or lift over drag curve, varies with the angle of attack. From this curve, we know that best efficiency is obtained at an angle of attack of 2 to 4 degrees. Let's see how this affects a propeller. As we have said, the angle that the blade of a propeller makes with the wind moving over it is known as the angle of attack. The actual direction the blade moves through the wind, which we will call blade path, is controlled by two factors: the speed of the propeller around the hub, known as propeller velocity, and the speed of the airplane, known as airplane velocity. The propeller velocity depends on the propeller RPM and also on the distance from the hub. It should be clear that point C, farther out on the blade, has a greater linear velocity than points A or B. Now, for any given propeller RPM, the propeller velocity will vary with the station or distance from the hub. The airplane velocity is the same for all parts of the blade at any one moment. So to maintain the desired angle of attack of 2 to 4 degrees at all points along the blade, it is necessary for the various stations along the blade to have different pitch angles. Thus we see that a propeller blade has the greatest blade angle near the hub A, and the least blade angle at the tip C. This relation remains constant for any propeller, regardless of its RPM or the speed of the airplane. So far, we have shown how propeller velocity influences the direction of the blade path. We've explained how propeller velocity changes with the propeller RPM and with the radius or distance from the hub. Here is a cross-section of a fixed-pitch propeller at a certain radius of station. The engine is running at a constant RPM, so the propeller velocity stays constant. At this pitch angle, the proper angle of attack of 2 to 4 degrees can be obtained only at one certain airplane velocity. If airplane velocity is higher, the angle of attack will decrease and the propeller efficiency will drop. If velocity is lower, the angle of attack will increase and the efficiency will drop again. This chart has shown that best efficiency is obtained by keeping the propeller blade at such a pitch angle that it is always somewhere near the 2 to 4 degree point in angle of attack. Right here, let's emphasize the distinction between pitch angle and angle of attack. As we have said, The angle that the blade path makes with the chord line of the airfoil is the angle of attack. The angle that the plane of rotation makes with the chord line of the airfoil is the pitch angle. In other words, the pitch is the bite of the propeller. Because of the twist of the blades, a certain radius or station is used to measure this pitch angle. This is the so-called 42-inch station. A fixed-pitch propeller is more practical on an airplane with a relatively small speed range. That is, a difference of only about 75 or 100 miles per hour between its maximum and minimum or landing speed. Its loss of efficiency is somewhat compensated for by its light weight and low cost. Looking back on the diagram of blade path and propeller velocity, we see that a fixed-pitch propeller on an airplane with a relatively small speed range will not get too far from the most efficient angle of attack. Fixed-pitch propellers of wood are carved for a specific make of airplane to provide the best pitch for its speed range. Ground-adjustable propellers with wooden or metal blades and steel hubs can be adjusted while on the ground to the best pitch for any particular airplane according to its speed range. Basic training type airplanes have a slightly higher speed range, in the neighborhood of 100 to 125 miles per hour difference between top speed and landing speed. This type of airplane usually mounts a two-position controllable pitch propeller. As the name implies, the pitch of this propeller can be controlled from the cockpit. From the blade path diagram, it is clear that a low airplane velocity, as at takeoff, requires a low pitch for the proper angle of attack. At higher airplane speeds after the takeoff, the propeller is shifted to a high pitch, so the angle of attack will remain close to the proper figure. The two-position controllable pitch propeller, therefore, is satisfactory on airplanes of medium speed range. This propeller is hydraulically operated by engine lubricating oil. By forcing the oil into the hollow hub, the pitch of the propeller is changed as the cylinder moves forward away from the hub. A propeller with a cylinder of somewhat flat end shape, blades, counterweights, and a small manually operated valve located on the crankcase nose can be identified as a Hamilton Standard two-position controllable pitch propeller. Airplanes with still higher speed ranges need greater propeller pitch ranges. In addition, they require intermediate pitch positions between the two extremes. This need is filled by the Hamilton Standard constant speed propeller. A governor usually mounted on the nose of the crankcase maintains the engine speed at a constant RPM as set by the cockpit control. Should the engine speed drop, the governor notes the change. It operates a valve, sending oil out to the propeller. This flattens out the propeller pitch so the engine can come up to proper speed. Just how this is done will be explained in subsequent training films dealing specifically with the Hamilton Standard constant speed propeller. Many medium-sized and large multi-engine aircraft are fitted with Hamilton hydromatic propellers, which have the additional property of feathering. In case one engine fails, that propeller must be capable of feathering, or turning its blades straight into the wind. For clarity, feathering is shown with the engine stationary. The blades offer less airplane resistance and act as a brake to prevent windmilling when flight is continued on the remaining engine. In some instances, windmilling has caused vibrations sufficient to actually tear the engine from its mount. Feathering also greatly improves the ability of the airplane to hold or gain altitude on its remaining operating engines. This propeller is capable of feathering in flight, and in addition has the constant speed advantages and the high pitch range of the Hamilton Standard constant speed propellers, counterweight type. The hydromatic propeller can be identified by its large oil dome with nut or breather cap on the end and by its governor on the nose of the crankcase section. Some aircraft mount still another type of controllable pitch propeller. The Curtiss electric propeller changes its pitch with a small electric motor mounted ahead of the hub. Constant speed operation is provided by a cockpit control which sets a governor. In the automatic position, this governor operates the electric switches to the pitch-changing motor. On multi-engine aircraft, a small switch in the cockpit allows feathering of the Curtiss propeller in flight to stop the engine and prevent damage. When the Curtiss propeller hub is concealed beneath a spinner, the propeller can be identified by the nameplate on the blades or by the control switches in the cockpit. Recently adopted by the Air Corps is the new Aero Products propeller, a hollow hub design permitting cannon installation. Each blade has its own pitch-changing mechanism in the hollow blade shank, a cylinder fixed to the blade, and a piston which, through helical splines, rotates blade and cylinder. Action of all three blades is synchronized by the coordinator gear in the hub, which meshes with a gear segment on the base of each blade. The propeller is entirely self-contained, with governor, oil pump, and pressure relief valve in one regulator unit just behind the hub. The Aero Products hydraulic propeller is found on later model Bell P-39 Aerocobras, where its hollow hub construction makes it ideal for the P-39's cannon. Because it is self-contained, the Aero Products propeller has no external identifying features. It has a propeller governor control quadrant in the cockpit, but no electric switches, as in the Curtiss electric propeller. Under the spinner is the regulator unit, the only positive identification of the Aero Products propeller. In summarizing the principles of propellers, keep in mind the distinction between angle of attack and pitch angle. Pitch angle is varied to keep the angle of attack constant as the direction of the blade path varies. The direction of the blade path is the resultant of two vectors, the propeller velocity and the airplane velocity. The high propeller velocity of the blade tip C produces a blade path at the smallest angle, so the pitch angle is smaller at the blade tip than at points B or A closer to the hub. That's why a propeller blade is twisted along its length. Likewise, when airplane velocity changes, the direction of the blade path varies. To allow for this, two-position controllable pitch propellers give the pilot a choice between low pitch or small bite for low speeds and high pitch or big bite for higher speeds. An automatic speed governor controlled by the pilot transforms a controllable pitch propeller into a constant speed model. By automatically varying the pitch of the propeller, it keeps the engine running at the specified RPM, a desirable feature from the standpoint of engine operation. Today, the Air Corps has many types of propellers for many types of airplanes. The highly complex propellers developed by recent engineering research have made possible more powerful engines in the faster airplanes we must keep for aerial supremacy.